sometimes when we have Lagrange multiplier questions, we aren't explicitly given the function that we need to optimize. So take a look at this problem. Find the point on the plane, x over 2 plus y over 4 plus z over 4 is equal to 1, closest to the origin in R3, closest to the point 0, 0, 0. So usually when we have Lagrange questions, we are looking for, we should see two formulas around, f of x, y, z, that is the function we want to minimize or maximize, and a g of x, y, z is equal to something. It gives us a constraint equation. But here we only see one thing. So x over 2 plus y over 4 plus z over 4, this point on the plane, this is equal to 1. This is going to be our constraint. G of x, y, z is equal to x over 2 plus y over 4 plus z over 4 is equal to 1. G is equal to 1. This is our constraint. So the thing that now we need to come up with is, what is our f? And the key word here to help us figure out what f is word closest. So what is closest? Closest means it's the shortest distance. Closest means it's the smallest distance, the minimum distance. And so this right here is going to give us the function that we need to minimize here. We just have to write it down. So we want to minimize distance subject to g of x, y, z is equal to 1, where I'm not going to recopy g of x, y, z right now, but it's right up there. The distance, what's the distance from a generic point x, y, z to the origin? Well, the distance is square root of x squared plus y squared plus z squared, our three-dimensional distance formula here. And so we could use the square root of x squared plus y squared plus z squared as our f function here. And then that would definitely work. But there's an easier way to do it. It will be a little bit messy to work with when we want to start taking derivatives of the square root x squared plus y squared plus x squared plus y squared plus z squared. There'd be lots of application of the chain rule and stuff like that. So the thing that we instead want to do is we don't want to minimize distance. We want to minimize distance squared, the square of the distance. And so we would get rid of, maybe I can just leave it like this and write this squared. And so in all actuality, what we're going to do, squaring the distance gets rid of the square root. We want to minimize f of x, y, z is equal to x squared plus y squared plus z squared, subject to the constraint g of x, y, z, x over 2 plus y over 4 plus z over 4 is equal to 1. And so at this point then, we can go ahead and use the Lagrange multipliers method. Of course, once again, this is written g of x, y, z is equal to 0. We want g of x, y, z is equal to 0. We could write it in that form, but all we're going to do is take, when we take the gradient, the constant will just go away. Okay, so let's go ahead and write down gradient f is equal to lambda times the gradient of g. So x squared plus y squared plus z squared. So the gradient f is going to be, the partial derivative with respect to x is 2x, partial derivative with respect to y is 2y, and then 2z, is equal to lambda times the x, y, and z partial derivatives are 1/2, 1/4, and 1/4 respectively. So 1/2, 1/4, and 1/4. Okay, so this is our Lagrange equation. let us just write this out as 3 separate equations here. 2x is equal to lambda over 2. 2y is equal to lambda over 4. And 2z is equal to lambda over 4. If we multiply, let's multiply the second and third equations by 2 to make all of them of the form lambda over 2 on the right. So this becomes 4y is equal to lambda over 2, and 4z is equal to lambda over 2. Lambda over 2 is also 2x. So we conclude that 2x is equal to 4y is equal to, 2x is equal to 4y is equal to 4z. Or dividing everything by 2, x is 2y is 2z, or we can write as x over 2 is equal to y is equal to 0, z. Okay, so now let's, we've gotten a relationship between x, y, and z here. Now let's pull back the g is equal to 1 here. And we do g is equal to 1. So we have x over 2 plus, I'm going to replace y and z both with x over 2. So x over 2 plus y over 4, but y, so x over 2 over 4 plus z over 4, but z is also x over 2. And so this is going to be, like this. And so when we crunch this out, we want this to equal 1. And we have x over 2, this is going to be x over 8 plus x over 8. And so then at the end of the day, what do we end up with? We end up with x over 2 plus, let's see, this looks like we are going to end up with 3/4 x is equal to 1, or x is equal to 4/3. Okay, x is equal to 4/3, y and z are both half of that. Y is equal to 2/3, and z is equal to 2/3. So we only have found one critical point. We've only found one critical point, 4/3, 2/3, and 2/3, and this must be the minimum. This must be the desired point. Find the point on the plane. X over 2 plus y over 4 plus z over 4 is equal to 1. Closest to the origin are 3. So the idea here, let me draw a picture. So we have, here is our plane, and so there is some point here. So 4/3, 2/3, and 2/3. This is the point that minimizes that distance. As we go further and further away from point off to infinity, there's no maximum. There's no point that gives us a maximum that's the furthest away from the origin, because we can always go farther and farther away. But this point right here gives us the minimum distance. So I think this is a good problem. This is a very useful trick, the idea of squaring the distance, and also the whole thing to watch out for. When you're not told exactly what your f function is, it's useful to realize that you can come up with the f function yourself.